And we're live. Okay, so y'all have out your notes from 3-7. Somebody talk to me about some of the things that you wrote down about this concept. What's the whole lesson about there?
I mean, like maximum and minimum values.
Okay, maximum, minimum values. Keep going, somebody else. The title was optimization problems. Okay, what does it mean to optimize something? Keith, what does it mean to optimize?
To like make it like, I'm guessing like make it in a way that you have a more perfect answer, I guess.
Okay, make it so you have a more perfect answer.
All
right. Vision, what would you say? What is optimize? If you were to optimize your practice routine, what would that mean?
Break it up or something like that.
Break it up?
Like in a way, like to make it simpler.
To make it what?
Simpler. Something like that.
To make it simpler? Okay, that might be like, that's more like a breakdown.
Yeah.
Okay. I think that might be part of it. Gabriella, help us out. Gabriella, help us out here. What does it mean to optimize something? Okay, make it more efficient. Mallory, how do you use the word optimize?
Like easier, like to understand, I guess.
Okay. Yeah, easier to understand. You know, fundamentally, the idea of optimization is you have some sort of process, okay, and you have inputs and you have outputs. And the idea is you want to get optimize the most output for a given input, or maybe the least output for a given output for a given input. Like maybe what might be something you want to maximize in sort of like a real world setting. If you were a business or involved in some sort of process, what might be something you want to optimize? Profits, money, the amount of money that you're making. So therefore, you might want to minimize. What might be something a business would want to minimize? Setbacks, lost time, cost, waste, inefficiencies. You want to minimize those things. And so you want to take all those things and minimize your output. And so of course, when we think about this in terms of graphs, we're thinking about in terms of relative minimum and relative maximum. So pretty much this entire chapter has been dealing with relative minimum, relative maxima, absolute maximum, absolute minimum, and then how to prove beyond a shadow of a doubt this is the absolute minimum. First derivative test, second derivative test, candidates test. How can we prove we know that this is going to be the best point? Maybe this is the I don't know, if you've got profits and this is the number of units that you would make. All right, we're going to make the absolute most amount of money if our company builds this many units. Okay, why? I'm like, well, you might say, well, if you make less, okay, I understand. If you make less and you sell less, you're going to make less money. But why is it that why would the graph of the amount of profits start going down if you made more than that? Okay, let's just say we've determined that we will maximize our profit, we'll optimize our profit if we make 100,000 of these doohickeys and sell them, whatever. But if we make 100,001 or 110,000, we actually are going to make less money. Why might you think that would be the case in a business?
So everybody will be buying it.
What's that?
Everybody's gonna be buying it, so they'll have it.
Okay, so everybody would be buying it, so they would already have one, and so the demand would go down. Okay, yeah, that's one way. Another thing is, if you found out, okay, if we can build 100,000 units, not dollars, but 100,000 of these units, that's all of our factories working, everybody working at, standard 40-hour work week. If we make more of those, we're going to have to start putting people into overtime. And if we start putting people into overtime, then we're going to have to pay them more, and then therefore our costs are going to go up, and so we're going to make less money. Does that make sense? Or we're going to have to be running the equipment more, and then we're going to have periodic shutdowns to retool and fix up our equipment. So we're going to lose money on that, and we're going to pay more maintenance fees. So it's not always the case is, well, just make more, and then you'll make more and more money. That's not the case. You have to take all of those things into consideration. So what we're going to be doing is beginning to kind of look at some real world applications for optimization. Unfortunately, we have to kind of start off with what I'd almost say are toy problems. They're not going to seem like toys at the beginning. If you looked at those notes, some of them weren't. The equations are pretty intense. But in order to really do this properly, we'd have to find a business and use multivariable calculus and utilize all sorts of crazy software, and we're just not going to do that at this time. But if you want to, there's lots of money to be made in finding how to make the most money. Turn in your book to page 222. There was a very interesting sentence at the end of it. It says, you must expect that real-life applications often involve equations that are at least as complicated as these 5, the ones that you took in your notes. Remember that one of the main goals of this course is to learn calculus to analyze equations that initially seem formidable. Yes?
There is no 16-year-old permission slip forms. Those were only for be tested for Zika.
That's all the stuff that they gave you?
That's what I told them.
Okay.
So 16-year-olds won't be able to.
Okay. All right then.
Okay, just giving you a heads up.
Appreciate it. So to repeat that, the purpose of this is to analyze equations that initially seem formidable. Okay, so it's one of these sayings: anything worth doing is normally not something that's easy. They say anything worth doing is worth doing well. That's true, but anything that's a meaningful problem is not an easy problem. Okay, so not everything can be reduced to just nice little 1/2 base times height. That being said, let's go ahead and look at some optimization problems. Now, the benefit here on this handout is that a lot of the work has already been done for you. So what we're going to do is we're going to ramp our way up. We're going to start off with these problems where there's a situation and they're going to tell us, this is what needs to be maximized, this is what needs to be minimized. They're going to give us the equation, even do some derivative and find some analysis. What we're going to be concerned with is mostly using one of our tests, maybe like the Candidates test or something like that, in order to solve this problem. So we're just going to put the finishing touches on it, okay? These actually are a little bit easier than the ones that we had, that y'all saw yesterday in the notes. So here we go. Instructions say, for each of these problems below, use the indicated method to prove that the given value is a maximum or minimum. All right, so here's a nice little agricultural example. A farmer has 80 feet of fencing to construct 3 adjacent rectangular pig pens, shown over here. Use the closed interval test. I'll circle that, put a little note on it. That's the Candidates test that we've been talking about. Some textbooks call it the closed interval test because it's got closed intervals, to show that the total area is maximized when the dimensions of each pen are 10 feet by 20/3 feet. What's 20/3? Anybody have that? Calculators? What's 20/3? You don't come on up here and get it. It's going to be 6 point something. 6.6 repeating. Okay. So I want to make sure y'all understand what the restrictions are. Okay. This farmer has 80 feet of fencing, and he has to have 3 rectangles that he wants to make out of that. He's going to share. He's going to have one big rectangle over here, and then he's going to have two other lines that you can do that. That way he's got three of them, they're right next to each other, we don't wanna make them separate. Why wouldn't we wanna make them separate? Levi?
More fences used.
Yeah, you have more fencing there, does that make sense? So we don't wanna, you'd have to use up this side, but if we can combine them, then that one side of fence can serve both purposes. Then all you have to do is just to hop over the fences, it's no big deal. So, what I want you to understand here is that there are lots of different options that this farmer has, okay? He could, with it, make these fences, you don't need to draw this, he could make them, these pens look like that. Okay? He can make them really thin. Or he could make them, really wide, like this. They all have to be the same. He could make them somewhere in between. There's all sorts of different, you make them just slightly a little bit more rectangular. Okay? Do y'all see that? In fact, how many different choices does he have?
Okay.
Yeah, he's got an infinite number of choices as far as fencing goes. But he doesn't want to, calculate, all right, what's the area that I'd have in here? What's the area that I'd have if I use this situation? What's the area that I'd have, you know what I mean? He doesn't want to spend forever doing that. He just wants to say, all right, what is the most area that I can build for my pig pens if I've got 80 feet of fence to work with? So his input, so to speak, is fencing, the amount of, well, not fencing, but, the amount of fence material that he has. Fence posts and maybe barbed wire, or if it's pig, it might have some wooden slats and things like that. The input is the amount of fence material that he has. The output is the area. Okay. Sometimes it's helpful to think, to write that sort of stuff down. The input is the fence material. The output is the area of the 3 pig pens. And he's trying to maximize area. So in almost all these problems, you'll need to draw a picture or something like that. They've got a nice picture shown here. And if there's any quantities or anything like that, we need to label them. So we've got X for the, we call the height that they have between them. Y, it would be the width of just one of those pig pens. So if we want to, it would be good for us to label, that's X, that's X, that's X, this is X, this is Y, this is Y, this is Y, this is Y, and that is Y. And the first equation that you can see that they wrote down, they said 4x plus 6y equals 80. All right? Because all of these sides added up together plus those must equal 80 feet. Then they rewrote that in terms of y. So y is equal to negative 2/3 x plus 40 over 3, just solving that equation. Then we have an equation for the area. They said they want to maximize area, but then this equation right here, I'll write a little bit larger here. Area equals 3xy. So the area is going to be, well, area of this rectangle, x times y, and there's 3 of them. So we've got 3xy right there. Now the trick is, on all these problems, is we need to have one concept in terms of another. Okay, so we can only have two variables, the dependent variable and the independent variable. In this case, I have area depends on both x and y in that case. So I need to do something to that equation so that it is all in terms of one variable. And that's where this equation over here, this y equals negative 2/3 x plus 40 over 3, I can substitute that in here for y, distribute the 3x, and that's how they have area is negative 2x squared plus 40x. Now I have the area completely dependent upon that side right there. And we're like, all right, I can handle this. I want to maximize that function. Well, how do you maximize a function? You take the derivative, they do that here, negative 4x plus 40, set it equal to 0, found out the x value, so x equals 10, okay? So x equals 10 is what we would call a critical point. Alright, now let's do the candidates test, okay? So if you remember, the candidates test says find all of your candidates and make a little table. So find, our x values and then plug those in to your function and then figure out which one's the highest, that's your absolute maximum. Find out which one's the lowest, that's your absolute minimum, okay? The candidates are always the critical points as well as, what else? Remember the candidates test? The endpoints, that's why it's called the closed interval test, so the endpoints. So we've got 10. The question is, what are the endpoints? What is the smallest x value and what is the largest x value that we could possibly have?
0.
Yeah, 0. X can't be any smaller than 0. It can't go negative. So, if that was 0, what would be the biggest value that x could be?
80.
80? Yeah, you might think so, but then you don't have three pig pens.
You divide by 3.
Well, you can't divide it by 3. Think about, as x gets longer, right, y gets shorter. Does that make sense? Okay, so this would be a very extreme example of a pig pen. Maybe the pigs are all lined up in a row, something like that. Okay, where y is very, very small. But could you make it even smaller than that? Yeah, you could. You could have y go down to virtually 0, but we would still have 3 pig pens. So, and we'd still have 4 vertical lines here. You see what I'm saying? So if y goes down to 0, and all 4 of these fences are just one right on top of each other, then it would be, then it would be like x, 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 x. Does that make sense? So in that case, x would be 20. Vision, does that make sense or not quite?
I don't get why it would be 20.
Okay. What do you think it might be? 80?
No.
Okay. If you use 80 for x,
Then it'll be.
then it's one really long line, okay? But you haven't made 3 pig pens. Does that make sense? So you need to have 3, you're like, well, if you have 4 sets of 20, they're really not on, it's still the same thing. But, well, it makes more sense if you can't go past 20, you certainly can't go to 80. But what I'm trying to just show you is, 80 is an unrealistic number, but in fact, anything over 20 is an unrealistic number. Because if you use 25, you have 25, 25, 25, that puts me at 75 right there. I'm only left with 5 left. Well, then I don't have a 3 congruent pig pens. So 25 is unrealistic. In fact, 20 is unrealistic. So that's why I'm saying 20 is our high-end value. Okay? Then what we're going to do is we're going to plug this in to our original function a. So negative 2x squared plus 40x. So I'm going to require y'all to do that here for me. Ladies, you take the 10. Guys, you take the 20. I'll take the 0.
Yeah.
20 is 0.
Like
200? Yep. What would the units on this be?
No, feet squared.
Yeah, per feet. Okay. Now, according to our calculations, we can be very technical at this point. According to our calculations, Farmer Joe, the maximum area that you will attain is if you have a vertical distance there of 10 feet for each pig pen. And if you make your pig pens, let's see, 10 by 10 by 10 by 10, how much does that leave him for these horizontal sections? 40. Okay, and there's 6 of them, so 40 divided by 6. Okay, so 6.6 repeating, so 6.6 feet, 6.6, 6.6, 6.6, 6.6, 6.6. Okay? So, hey, what do you know? That's what it says in the problem. It says, use the closed interval test to show that the total area is maximized when the dimensions of each pen are 10 feet by 20 feet. You're like, I already knew that. It was in the prompt. Yeah, the problem wasn't find the maximum. The problem was prove it. Because Farmer Bob over there across the way is like, you know what? I bet you if you put 15 feet there, it's going to give you more area on your pig pens. And Farmer Joe's like, nope, got those calculus students there to run the numbers for me. Paid them $200 an hour to get that done. Okay, so it really doesn't require that much. But if you don't know calculus, it can seem kind of strange. But the nice thing is that we can absolutely know that this is what's best for him. Now, if you're in my engineering class, we found out, hey, you know, even though you've got the most, this is the absolute best scenario, there might be some other things he's got to take into consideration, you know, and you've got to put those in, you know, that's, we're talking with Farmer Joe here will be helpful. But as far as mathematically perfect world, there you go, that's his best scenario. Anybody have a question about what we did there? Okay, let's look at another one. Levi, go ahead and read that off to us, number 2.
If a rectangle box with a square base and an open top is to have a volume of 4 cubic feet, use the first derivative test for experiment to prove that the dimensions that require the least amount of material are 2 by 2 by 1.
Okay. So, we want a box that's going to hold a volume of 4 cubic feet. Maybe we're trying to transport something or wanting to move something from one place to another. Maybe it's liquid, maybe it's sort of semi-liquid, like some sort of gel. But we know that it'll fit in 4 cubic feet as long as it's 4 cubic feet. It doesn't need a top, so whatever is not going to spill out or anything like that. We want to use the least amount of material for the sides. Why do you think they might want the least amount of material for the sides? Why would a company maybe that's making these boxes?
Save money.
What's that?
Save money.
Yeah, save money. All right. I mean, it's going to cost you materials and building costs to put all this stuff together. So you want to try to minimize the amount of material. Maybe it's cardboard, maybe it's wood, maybe this is, you know, something, you know, very, you know, this is toxic waste, and so we need to have some, you know, special polymer box here. But that gets better to put the top on it. But anyway. Who knows what we're trying to do? We want to minimize the surface area. Very, very real situation that businesses face. So you can see here what they've done is they've got the picture. They have it's a square base, which you can see that's underlined, which means that you've got this side is X and that side is X, and the other ones are as well for that matter. And they say X squared times Y equals 4. That's the volume formula, okay? Because you've got X squared, it's that area of that base, formulas for area of the base times the height. So times the H is equal to 4. That's the equations that's going to relate everything. Then, because they know where they're going, they actually took the Y and solved it for X. So Y equals 4 over X squared. They want to minimize M. They put M for material, I would have put maybe S or SA for surface area. So the surface area of this, if we write it out the long way, it's going to be this bottom, which is x squared, plus 4 sides. So y times x, y times x, y times x, and y times x, which is why they say 4xy right there. All right, so once again we have our value which we're wanting to minimize. I would write it over here. Minimize surface area, which is what they're calling M. And we've got 2 variables, or 3 variables technically, the material, x, and y. They'll utilize this formula right here and substitute that in for the y value, which you will have to do when you do this part of the problems on your own. So wrote that as 4 over x squared. Just multiplying that out, we have m equals x squared plus 16 times x to the negative 1. We're going to use the first derivative test. So to find the first derivative, derivative x squared is 2x, derivative 16x to the negative 1 is negative 16x to the negative 2, which then they rewrote as 2x minus 16 over x squared. Set that equal to 0. And when they did that, they brought the 16 over x squared over here, multiplied both sides by x squared, so 2x cubed equals 16, divided by 2, x cubed equals 8, x equals a positive 2. All right? So, first derivative test, normally what that involves is writing f prime, little sign chart, and we'll put 2 right there. That's our only critical point. So we need to plug in a value to the left and plug in a value to the right. So a good value over there would be 0. A good value over here might be
4.
not 1.
Unknown.
3. Okay, great. Y'all are extremely verbal today. Appreciate it. So
You
yeah,
said 4.
you said 4. Okay, all right. Well, I'm sure they heard it. All the way at the front, I couldn't hear it, I guess. So, all right. So we'll plug in 4 for vision there. All right. So I'll take care of the 0. Y'all take care of the 4. We are plugging it in. I wrote f prime. We probably wrote what that is. M prime. What you're going to plug that into is this equation right here, 2x minus 16 over x squared. We're going to figure out whether or not it's positive or negative. And I'm plugging in 0, and I'm going to get a 0 in the denominator, and so that's not good. I'm going to plug in 1. So I have 2 times 1 minus 16. I'm going to get negative 14. I get a negative number. What do y'all get?
I know.
Okay. Would y'all agree something positive? Okay, I would concur. So since m prime is negative here and positive here, if we wanted to, we could put m above that, which, yep, surface area is decreasing as long as x goes up to 2, and then it is increasing after that. So to prove this one, we might need to add just one short little statement. It was a very small part of our notes, but we could say x equals 2, or we could say since x equals 2 is the only critical point, and m prime goes from negative to positive at x equals 2, then the surface area has an absolute, not max, minimum at x equals 2. That's a way that we can actually say it's the absolute minimum and we know it for sure. And the reason is because that's the only critical point. You might say, well, why does that really matter? Because if it wasn't the only critical point, then even though it's increasing at this point, at some point later on down the road, it might go to decreasing again, and it might drop even lower. But if it's always increasing, if the surface area is always increasing after that, then we know that 2 is going to give us the minimum amount of surface area here. So they went through just one extra step and said, okay, so that means this would be 2, that would be 2, and y would have to be 1 since you have x squared times y equals 4. So that's going to be the dimensions of the box, which is going to give you the minimum surface area. Okay? So calculus here is used not only to sort of find the absolute minimum or the absolute maximum, but to prove it. Okay? That's where it really comes into be like, hey, it's pretty low right here, but how do I know it's the lowest? Well, this is the lowest. Well, how are you sure? Well, the first derivative test guarantees that this is going to be the only point, the only critical point, and therefore the only place where the surface area is at a relative max or relative min. In this case, that turned out to be also an absolute max min. Do y'all see how this is kind of helpful with maybe businesses? Yeah, hopefully yes. You say, don't they have computers for that? And the answer is, yeah, they do. They have computers, and guess who tells the computers what to do? People who know calculus, all right? Well, how do they know if the computer is right? They have to check it with people who know calculus. Those of you that took my programming class, remember we had to do test data, right? You test in my programming classes. You have to do test data. You have to do all the calculations by hand to make sure that your program is working properly. Otherwise, it could be spitting out answers and you have no idea what the heck, whether it's right or wrong. So, whenever they walk in, go ahead and hand that to me. All right. Let's look at another one here. The paper one's not too bad. I guess we'll look at this one.
Did you write what was on the paper? Or was that already written there?
I did not write that. That was someone who was, extremely excited about calculus. Do you want to read that to us? Okay, well let's sort of a hidden message there. Mallory, read to us about this paper here.
A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are each 1/2 inches, or 1/1/2 inches. The margins on each side are 1 inch on the figure. Use the second derivative test for extrema to show that the least amount of paper is used when the dimensions of the page are 6 inches by 9 inches.
Okay. Oh, paper. Who uses that stuff anymore? All right, printing on paper. Okay, yeah, true. I mean, there's that. That might not be the situation.
Paper.
Okay, that is paper. You're right. I did not use calculus to figure out the maximum or minimum here, but what might be an industry or a business that is interested in something kind of like this, maybe minimizing or maximizing the amount of white space or content space on some sort of medium. Who might want to, what we're trying to do, we're trying to say the least amount of paper is used. So this person is concerned with not using a lot of paper, okay? Or maybe concerned with maximizing the content space. You might be interested in transferring some sort of information through any media, okay, that people can see.
Newspaper.
Okay, newspapers, okay. Let's move it up into your generation. Magazines as well, yes, absolutely, that's great. If you want to go one route, we could say advertisers, if they're making a sign, if they're making a billboard, if they're making anything like that, they are going to want to get as much as much material there as possible. Hello, web pages, right? Okay, I mean, advertisers on web pages. I mean, that is, you know, space is at a premium in terms of pixel size. They want to get as much as you can on there. And then here's where the real money is made, is if you can create an app or a software package that will automatically maximize or minimize the space, you know, as well as keep everything in the correct proportions and whatnot. Then all the people, you know, then whoever's doing the designing doesn't have to worry about knowing the calculus. They just hit the little optimize button at the top, and it will adjust, you know, all the different things, you know, going on side, maybe the pane or you know, whatever's going to be on the display screen or whatever. Okay, we're going to use paper just because that's the way this example has, but I want you to see that there's a lot of other examples here where this would correlate to. So we've got just enough time to look through this one. Just like you said, the paper has, there's 24 inches of print. All right, so that's this by that. So we're gonna have an X and a Y, some sort of rectangle. Multiplying those two together, you're gonna get 24. They went ahead and solved that for X, or solved that for Y rather. Then you've got margins. The margins at the top and bottom page are 1.5, which means you've got you know, 1.5 here, 1.5 there. You can see if you add that 1.5, 1.5, then you have this whole X value plus 1.5 plus 1.5 plus the 3. Y right there is the text, and you've got 1 inches on the side, so you got 1 inch on either side, which is why the whole paper there is Y plus 2. So we're wanting to minimize the area of the paper, the whole thing. So that would be the whole length by the whole width. So X plus 3 times Y plus 2. Once again, we have multiple variables, so we need to plug in 24 over X right there. They distributed all of that and have 30 plus 2X plus 72 over X. And then you have this right here. They just wrote it as X to the negative 1. Took the derivative, set it equal to 0. Found out that that's going to give us, et cetera, down here, an X value of 36. So that's our critical point. Here they say, use the second derivative test, okay? Well, that means we need to find the second derivative. I've got a prime right there. Let's very quickly find the second derivative. So looking down here, the derivative of 2 is 0. Bring this, pop down that 2, so negative times negative 2. So that's just going to be a positive 2 times 72 times X to the negative 3. So that's going to be 144 over X cubed. If you remember the second derivative test, okay, actually we don't do that bar chart. We just plug in our critical point. So a double prime of 6 is going to be 144 over 6 cubed. Is that going to be positive or negative? Positive. So a second derivative which is positive tells us that our original function is concave up, I believe. Yeah. So it's going to be concave up. Since we're concave up, then our critical point must be what? A minimum. So we'll say since X equals 6 is the only critical point and a double prime of 6 is less than 0, we would say the absolute minimum area occurs at X equals 6 by the second derivative test. Since X equals 6 is the only critical point, and the second derivative is negative at that point, then that must be an absolute minimum. And then they went ahead and plug in 6, all right, for the X, then then, you know, the Y has to be 24 divided by that, 6 by 9 inches. Oh, that's the actual page number, so.
Doesn't make any sense.
That doesn't, I
Oh.
don't think that I don't think that 9 is the proper number there, I think
Yeah,
it's
yeah,
4.
it is, cause, wait,
We're saying that X equals 6, Y would equal 4,
it'd be 6, yeah,
so
it's
X
gonna be 6
equals
by
6, Y is 4.
It'd be 6 by 9.
Add 3, so you have 9 for there, and you add 2. Okay, there we go. That does make sense. Alright, your homework is just to do the 3 on the back of that page. Alright, thank you for watching. I got a video to watch, and just like you were here the whole time.